Okay, this is number 32 on 3.2. And what you're trying to find over here, number 32, is find all values of x for which the function is differentiable. And basically this looks like this is okay, except we have to remember our when we have a cube root, we do have a point where there's a possible vertical tangent when x equals 0, or when we're taking the cube root as 0. If you remember what it looks like, it's kind of like that little s that goes up. You know, if we kind of remember what it looks like, let's see. Kind of goes like this. Remember, it goes up like this, and it goes straight up like that. Okay. Get a pencil here, sketch something for you. So it looks something like this, remember. So this was y equals the cube root of x. This was one of our parent functions. So we're interested in what's happening right here, and that was at the 0 point. So that's when we're taking the cube root of 0. So what we want to do is see what happens when this is 0. Well, if we set this equal to 0, we get x equals 2. Everything was okay except we might have a vertical tangent there, so that's what we want to look at. Okay, so you have to kind of remember your parent functions. We know we had kind of something that's going up like that, so is that indeed a vertical tangent? Or do we have a slope? So we take the left-hand derivative of this function. So that's going to be f and my point. Now this is going to be 0 when x is 2, so I'm going to be dealing with 2. So my a will be 2. So I can say a will equal 2. And I didn't write down the first formula, I just wrote down the second part when I actually substitute the 2 in. And this was kind of a complicated, so this is going to be 2 plus h. I've got to put 2 plus h in every time I see an x. Right? So 2 plus h here. So 3 times 2 plus h minus 6 plus 5. That should be minus 5. That should be plus 5. See, did I write it down correct? Let's see, where did I copy it down wrong? 32, that's plus 5. So that should be plus 5 here. Sorry about that. That's plus 5, so this is plus 5. And that's plus 5. So this is going to be plus 5. And this will be minus 5. Sorry, I made a little mistake there when I copied it down. Okay. All right. When I transpose it, excuse me. All right, so we've got this. And then when I put 2 in, it's just going to be 3 times 2 minus 6 plus 5. Okay. Then we can go over here and simplify it out a little bit. And this is going to be 3 times 2 is 6 plus 6h. I'm sorry, 3 times 2 is 6 plus 3h minus 6. That's all under the radical. Plus 5 minus the cube root of 3 times 2 is 6 minus 6 plus 5. And that's nice because that just becomes 0. So, and this becomes, the 6's cancel. So I've got the cube root of 3h. So this all becomes just the cube root of 3h plus 5. This is 0, so that's just plus 5 times the negative is negative 5. And the 5's cancel, so we end up with this. Okay. And then I can break this up into 3 to the 1/3 times h to the 1/3 over h. And I can bring the 3 to the 1/3 out front, and I've got this limit. This looks kind of like what we've been doing before. We'll bring this down to the bottom, and we've got 1 over h to the 2/3. And we've got the 3 to the 1/3 out in front. That's just a constant. That's not going to really affect much when we get out to infinity. So we're going to do a very small approach as we approach 0 from the left, because this is the left-hand derivative. So it's 3 to the 1/3, limit of 1 over, and then we've got negative, very small number, negative 0.00001 to the 2/3. I've got this 3 to the 1/3 out in front, 1 over, and I've got this. And I could break this up into negative 1 to the 2/3 times that very, very small number, positive to the 2/3. But again, the cube root of negative 1 is a negative 1 squared is 1, so that's just 1, so that becomes absorbed. That's a positive 1. So I've got this, and then this is just like 1 over infinity. So I've got 1 over 1 over infinity. to the 2/3, 1 to the 2/3 infinity to 2/3, which is again 1 over infinity, so that just becomes, ends up, this is our infinity, and this is 3 to the 1/3 times infinity, which is just infinity, so I end up with a positive infinity, bottom line. Okay, then I kind of abridged my work a little bit because we've done these so many times now. So we could see that the limit, the right-hand derivative of this limit as h approaches 0 of this is all going to simplify the same exact way. It's all going to simplify. We're going to do all the same steps. Everything's going to be the same except we just have a plus here. So everything's the same until we get down here. So this is, I just went from this step to this step. So this actually eventually simplified to be this, just like it did in the left-hand derivative. That was just to save some time and space. I'm sure you'll appreciate that. Okay. And then again, we can think of this as a very small approach, except this will be approaching from the positive. So this would be just a positive number. And I've got this 3 1/3, and I've got 1 over infinity, and then we do the same thing. That's to the 2/3, that's 1 to the 2/3 over infinity 2/3, which is 1 over infinity again. So it just becomes infinity, and that's 3 to the 1/3 times infinity, which is a positive infinity. So in both cases, I get a positive infinity, since both one-sided limits go to positive infinity. Oh, I'm sorry, I was babbling on here, pardon me. Excuse me, I covered up my work. So we could take a look over here. Again, this is the same work. And then again, this is 1 over, very small number, 2/3. So that becomes 1 over infinity 2/3, 1 to 2/3 over infinity 2/3, as I spoke through. 1 over infinity, which is just 3 1/3 times infinity. That's another positive infinity. Sorry, I wasn't watching what I was doing. And since both one-sided limits go to positive infinity, I have a vertical tangent at x equals 2. So hopefully that will help for number 32.